Everyone, the column is located in front of the FKTA office building, shows visible vertical and diagonal cracks along its surface. These cracks are signs of structural distress and may have been caused by several factors such as concrete shrinkage, foundation settlement, overloading, or exposure to environmental conditions over time.
Non-destructive testing, NDT, is a method used to assess the condition and quality of materials or structures without causing any damage to them. In civil engineering, NDT is especially useful for evaluating existing buildings, bridges, or concrete elements where preservation is important. For the Dragon building at Pusat Pengajian Jejawi 3, several NDT methods were used to inspect a selected structure. These include rebound hammer test to check the surface hardness and estimate concrete strength, moisture test to detect water intrusion that can affect durability, crack monitoring to observe the size and movement of cracks over time, resistivity test to assess the risk of steel reinforcement corrosion inside the concrete.
The rebound hammer test was conducted on two sides of the selected concrete structure to evaluate the surface hardness and estimate the compressive strength. Based on the results, side 1 recorded an average rebound number of 21, corresponding to an estimated compressive strength of 11.18 megapascal, while side 2 recorded a significantly higher average rebound number of 36, indicating an estimated compressive strength of 32.78 megapascal. The disparity in results between both sides is notable. Side 1 shows significantly lower strength, which is likely due to the presence of visible surface cracking and surface deterioration.
The moisture test was conducted on a reinforced concrete column to evaluate the internal moisture content, which can be an indicator of water ingress, potential deterioration, or conditions conducive to reinforcement corrosion. 5 readings were taken at different spots on the column, and the average moisture content was found to be 1.5%. This value falls within the normal range for concrete in indoor or sheltered conditions. Typically, moisture contents below 3% are considered acceptable for reinforced concrete and do not pose significant durability concerns. The relatively consistent and low readings also suggest that there is no active water leakage, seepage, or severe environmental exposure affecting the structure at the time of testing. Additionally, the absence of surface efflorescence, mold, or damp patches further supports the conclusion that the column is not exposed to excessive moisture. However, continuous monitoring is recommended, especially in older buildings like Dragon, as microcracks or poor waterproofing may allow moisture ingress over time. Conclusion: the reinforced concrete column shows no signs of abnormal moisture content. The structure appears dry and in good condition with respect to moisture, indicating no immediate risk of corrosion or moisture-induced damage.
The resistivity test on the concrete column revealed values of 1210, 1216, 1250, 879, and 1380 ohm cm, resulting in an average resistivity of 1187 ohm cm. This average indicates a low to moderate risk of corrosion for the embedded steel reinforcement, suggesting that the concrete generally possesses adequate durability and resistance to moisture and chloride penetration. However, the fourth reading, 879 ohm cm, is noticeably lower than the rest, which could indicate a localized defect or area with higher moisture content, reduced compaction, or poor concrete quality.
Crack monitoring is the process of observing and measuring cracks in concrete to evaluate their development over time. It plays a crucial role in identifying structural weaknesses and assessing the impact of environmental or mechanical stress on the material. Techniques such as visual inspection, microscopy, and digital image analysis are commonly used to measure the width, length, and propagation of cracks, providing valuable insights into the durability and condition of the concrete.